Yesterday we recapped discrete random variables. We're now interested in looking at the continuous ones, and what's the difference? Let's compare the two. So this one is of course discrete, the probability distribution, number of heads obtained when you toss two coins. So possible outcomes 0, 1 and 2, probability of each a quarter, a half and a quarter. Remember, x is the random variable. I'm defining that for this problem to be number of heads tossed. Our probability function is probability x equals x there. I'm going to introduce a new function here called the cumulative probability function. I'm simply going to call it f, so capital F. And what it represents is the probability that x is less than or equal to a certain value. So it's like the cumulative probability up to that point. So in some notation, it will be t equals, well, I put a there because it just depends what the first case is. So for ours, it would be t equals 0 to x. But I mean, there's nothing to say that the first case is going to be 0. It could be something else. So a is just representing whatever the first case is. And so for ours, if I was to find function 1, well, the cumulative probability going up to 1 is 3/4. So that would be our function f there. So cumulative probability function, also known as the cumulative distribution function. What happens with a continuous random variable though? Here's the really interesting thing. It's not possible to create a probability function. And I'll use this as an example, height of adults, which would be continuous. So between any two values, let's say 170 and 175, there's an infinite number of possibilities. Because theoretically, you could break it down to smaller and smaller and smaller units. So interestingly, if I wanted to find the probability that x equals 172.4, the answer is actually 0, which I know sounds weird. Like there's no chance that someone could have a height of 172.4. Here's the explanation why. If I've got the number of people being 172.4, let's say there's 23 people that actually are of that height. So there's 23. But how many possible measurements are there between 170 and 175? Well, there's an infinite number of measurements between there. So by our probability theory, it would be 23 over, well, infinity. Well, I've written that as the limit as n approaches infinity because you can't actually substitute infinity in. But we also know when we're finding limits, with something like this, the limit's going to be 0. So the probability actually ends up being 0. So this is a weird thing about continuous distribution. If you want to find the probability of a single value, the answer is always 0. There's no chance of it happening. Weird. So how do we deal with it? Well, we're going to use relative frequencies and putting data into classes. How we grouped them into classes. Then that will allow us to treat continuous data as if it's discrete data, and we know how to handle discrete data. So let's use this as an example. X is representing the amount of time we have to wait for a ski lift. And so it's somewhere between, you can go straight away, up until 5 minutes. Now, if I want to find the probability that the random variable is in between 1 and 3, there's different ways I could do it. I could use the relative frequency. So you notice my table now is a relative frequency table rather than what we had before. So relative frequency, 0.214 and so on. And then I've got a cumulative as well. So adding them up as we go. So I could just look at the relative frequencies and say, well, if I want to go in between 1 and 3, it's going to be 0.196 plus 0.210. I get 0.406 is the answer. Another way I could do it is to use our graph. If I use that histogram, remember yesterday we saw that the probability turns out to be the area of the histogram if the width is 1. And in this case, you'll notice the width is 1. It's going 0 to 1, 1 to 2, 2 to 3, and so on. So I can use those areas. Well, those areas actually turn out to be the same as those probabilities. So again, we get 0.196 plus 0.210, which is 0.406. So that's a second way we could do it. Now, third way, I could use the relative frequency polygon, because also you recall yesterday we said the area under the polygon would be the probability. So if I'm going from 1 to 3, I'll use the trapezoidal rule to come up with that, and we actually get a little bit more accuracy there, 0.40575. But again, that's 0.406, same answer to 3 decimal places. A fourth way is to actually use the cumulative relative frequencies, and so this new function that I introduced. So if I'm going in between 1 and 3, I could say, well, it's going to be function 3 minus function 1. And then I read those values off. I'll get 0.620 minus 0.214, and then again, 0.406. 4 different ways there we could come up with the answer. But then the question comes on, well, how would we find in between 1.5 and 2.5? Well, I just change the class widths. If I now bring them in to be widths of 0.5, and I'll redo the table, and again, each of those methods will come up with the answer. So relative frequencies, we've got 0.207. I can find the area of the histogram, but this time I've got to be careful, because you notice the widths of my histogram are no longer 1. They're now a half. So they will add up to be half of the probability. Therefore, I've got to multiply my answer by 2 to make sure that all the probabilities add up to 1. So we've got to be careful with that method if we're doing the area of the histogram. The polygon, so again, using our trapezoidal rule, and we come up with 0.20675, which to 3 decimal places, yes, that is 0.207. And using the cumulative frequency function that we came up with, function 2.5 minus function 1.5, 0.207. So we do that. So that now brings up the question. If I can just keep reducing these class widths, what would happen if I made the width of the class, well, I can't actually make it 0, but what would happen if it's approaching 0? Then what should happen is that area under the polygon will approach the area of the histograms. That's what we were talking about yesterday. We want that to be exactly the same. So function B minus function A. The difference in that new function I just talked about, the cumulative distribution function. Now this is where stats gets exciting, because now we start using calculus. And so you might be wondering, why on earth is statistics in this course, which essentially is a calculus course? And this is why. It's a use of calculus, the stats. So probability density functions. And it's the equation of the relative frequency polygon. So the equation of that curve. Here's our properties. Well, function x is greater than 0, again, because we're talking about probabilities, we know they have to be positive. We know that if we had every possible outcome, so if we went from minus infinity to infinity, all of those probabilities should add up to be 1. So the area under that curve should be 1. But usually we're finding between particular values, so we would just simply integrate that function from A to B, the 2 values that we want. Here's an example. A bid's being made in auction for a real estate property in millions of dollars, and it can be modelled by this random variable x. And here's our function. We're saying, well, in between 1 and 4, it's going to take on this value. Anywhere else, it's going to have a probability of 0. So if I want to work out what k is, well, I know minus infinity to infinity should total 1. But for ours, I only have to worry about between 1 and 4, because everywhere else it's equal to 0, and we know the area under the curve, if we're talking about the x-axis, is 0. So I don't need to worry about that bit. So I'm just going to integrate from 1 to 4 of this function, and I can find that value of k. And there it is, 1 on 27. So just a bit of integration. So let's go and find that cumulative distribution function, and you might have picked up on it, but why did I call it capital F? Because capital F is what we used for primitive function. And that's essentially what we're now doing. We're finding the primitive function of this. So integrate from 1 to x, because remember the starting point for ours was 1. So 1 to x of 16 minus x squared. We integrate it and we come up with the function. So there it is. Before we get to 1, we know the answer is going to be 0, because there's nothing there. In between 1 and 4, we will have this function, but after 4, well, the probability's got to be 1. Remember, it's cumulative. Once we've hit 1, that's the most it can be. So everything after that has got to be 1 as well. And we have our function, which will now allow us to solve different probability and stats problems. So, what is the probability that a bid of more than $3 million will be made? So in other words, when X is representing the bid, we want to know when it's greater than or equal to 3. But we're dealing with a cumulative one. So using the complementary event idea, I'll say, well, hang on, that's the same as saying 1 minus all the ones up to 3. So 1 minus our cumulative function there of 3. I sub into the formula that we've worked out, and I get the probability. It's 11 on 81 for this problem. So how do we find quartiles? Well, they're important statistical measures. How would we find quartiles? Well, we know they represent 25%, 50%, 75%. So to find the Q1, I would integrate from minus infinity to Q1. I know that's going to be a quarter, because 25% of the data must be there. To find the median, well, minus infinity to m, that answer should be a half. And then Q3, that answer should be 3/4. Here's our function that I'm going to play with for this one. It's median, so what I'm saying is 1/9 of x squared, it's going to start at 0. So from 0 to the median must have half of the data. So that has got to equal a half. All right, bit of integration, and we solve it. It's a beautiful number, 3 on the cube root of 2, but I suppose in stats we don't usually leave things as exact values as much as it annoys me. So 2.38. 2.38 would be the median for that particular problem. Well, what about the mode? The most frequent. Here's the function. Well, it's a quadratic. So I don't actually have to use calculus this time. Because essentially we're saying, what's the maximum of this quadratic? When will it happen? I don't actually want to know what the maximum is. We want to know the x value, because that's the mode. And it's going to be the axis of symmetry of the parabola we've got. So minus b over 2a, we get 1. So the mode of this one is 1. Now, yeah, okay, I picked a quadratic to make life easy for myself. If we didn't, then of course we could use our calculus to find maximum turning points and things like that. And that would allow us to find the mode. So 16b is now where we actually start introducing calculus into our statistics.